June 7, 1940. At Chrysler's Highland Park headquarters in Michigan, a 7-minute telephone exchange that would alter the course of modern combat. William Knudsen, President Franklin Roosevelt's freshly appointed Commissioner of Industrial Production, asked an almost absurd question: could Chrysler manufacture tanks? On the other end sat Kaufman Thumacella, Chrysler Corporation's chief executive, who replied with blunt candor, "I don't know. I've never seen one of these things." At that moment, the U.S. Army possessed exactly 66 medium tanks. In contrast, Nazi Germany had unleashed over 3,000 panzers across Europe in barely more than a year, annihilating Poland in 26 days and overwhelming France in 6 weeks with coordinated armored attacks. America's modest tank inventory could have been wiped out before noon on any given day of the Blitz. The arithmetic of defeat was already being inked in blood on European soil. What neither Knudsen nor Keller realized was that their brief call would spark the most dramatic industrial shift in military history. 9 months later, Chrysler achieved a feat unimagined by traditional armories. 30-ton tanks machines that had once required months of skilled artisan work began to come off production lines with the regularity of cars, at peak output one every 55 minutes. The innovation demolished long-held beliefs about armament manufacture and demonstrated that American industrial know-how could turn production itself into a weapon. The struggle started with a basic reality. In June 1940, the United States ranked 19th in military strength. Trailing nations like Portugal, its army still relied more on horses than tanks. The Ordnance Department, charged with weapons development, used production methods virtually unchanged since World War I. Tanks were hand-assembled in government arsenals, each a bespoke creation, demanding master craftsmen. The Rock Island Arsenal in Illinois might crank out perhaps 3 medium tanks a month at full tilt, each taking 12 weeks from raw material to combat readiness. Germany's panzer output relied on similar craft techniques, but benefited from years of surreptitious rearmament. By 1940, German factories were producing about 1,400 tanks a year. Britain, although farther along in mechanization than the U.S., managed only about 1,000 tanks annually. Major powers treated tanks as complex weapons that required expert builders, specialized plants, and many months of careful assembly. After the call, Keller phoned his chief engineer, B. Hutchinson, and Frank Zeta, Chrysler's vice president of engineering. Within the hour, the 3 men met in Keller's office to confront an almost impossible brief. The Army demanded 1,000 medium tanks within less than 18 months and expected Chrysler to erect a factory, devise production methods, and deliver finished vehicles, despite starting from zero tank building experience. Hutchinson's first question hit the core. What is the current production tempo for a tank? Zeta had done his homework. Rock Island was producing 3 M2A1 medium tanks a month, each taking 12 weeks, assembled by skilled craftsmen with hand-fitted parts. Hutchinson ran the numbers. At that pace, producing 1,000 tanks would take 277 years. The Army wanted them in 18 months. Keller set the program's guiding principle. We won't build tanks the Army's way. We'll build them our way. If they wanted 1,000 in 18 months, Chrysler insisted, they must accept automobile production techniques and be willing to let us see and standardize what we're making. Within days, the trio toured Rock Island Arsenal, observing workers hand-fitting armor plates, judging track tension by eye and experience, and custom machining parts to compensate for wide tolerances. The M2A1 medium tank weighed about 19 tons and mounted a 37mm gun. Assembled from roughly 8,000 components, manufactured 2 loose tolerances that forced skilled fitting. No 2 tanks were identical. Keller saw the central flaw at once. This wasn't scalable manufacturing, but rather sculpture. Every piece depended on a craftsman's touch. You couldn't rapidly train enough workers or ramp output to meet the Army's deadline. Back in Detroit, they formed a secret tank committee, a daily, often all-night working group in a commandeered Highland Park conference room, bringing in Owen Skelton, Chrysler's chief production engineer, and specialists in tooling, metallurgy, and logistics. Their epiphany came from flipping the question. Instead of how to speed up existing methods, they asked how to build tanks in a different way. Skelton framed the idea. An automobile is a few thousand pounds of metal, rubber, and glass assembled from about 5,000 parts. We make some 3,000 cars per day at Highland Park. A tank is heavier and uses perhaps 8,000 parts, but it's still just a mechanical assembly. If seen that way, automobile production principles could apply. That realization forced a ground-up redesign. Every part had to be re-engineered for mass production. Assembly sequences rethought for line work, and quality control converted from craftsman's subjective judgment to measurable specifications. Their analysis of the M2A1 showed roughly 60% of production time went to custom fitting and adjustments because arsenal tolerances varied so much that assembly demanded constant improvisation. Hutchinson proposed a radical fix: manufacture every component to automotive tolerances so parts would fit together without rework. Military engineers objected that tank parts endure stresses far beyond automotive components, and that achieving such precision required new tooling, new suppliers, and new QA methods. Yet the potential payoff was enormous. A vehicle that took 500 man-hours to assemble with hand-fitting might be reduced to about 150 man-hours if precision parts simply bolted together. Skelton extended the idea. If tanks were to be treated like cars, they needed an assembly line, a moving line that brought work to specialized stations rather than craftsmen clustered around a stationary hull. By November 1940, the committee had codified the Chrysler method for tank manufacture, machine every major component to precise tolerances with automotive tools. Standardize and make armor plates interchangeable. Weld hulls using production jigs instead of hand-fitting. MOUNT turrets on standardized rings. Reuse automotive drivetrain components where possible. And perform final assembly on a moving line with dedicated workstations. Keller presented this method to the Army Ordnance Department that month, too skeptical, even hostile. Reception, automotive tolerances were deemed insufficiently rugged for combat. Moving lines were feared to create QC issues. Welded armor was criticized versus rivets. And a target of 10 tanks per day sounded fanciful. Keller's unanswerable retort was simple. You need 1,000 tanks in 18 months. We can do it, can anyone else? The Ordnance Department had no affirmative reply. In late November 1940, Chrysler was awarded an extraordinary contract. The Army would fund construction of a purpose-built tank plant, and Chrysler would design, outfit, and operate it. The Army stipulated one more condition. The new factory had to be designed by Albert Kahn, the Detroit architect who had reshaped factory design with projects like Ford's Highland Park and River Rouge plants that enabled mass automobile production. Kahn, then 71, a German-Jewish immigrant who had come to Detroit in 1881 and learned architecture through apprenticeship rather than formal schooling, led a firm of 600 architects and engineers and by 1940 had designed nearly a fifth of the nation's architect-designed industrial plants. His genius was to treat factories as machines, maximizing daylight, optimizing material flow, creating column-free spans for flexible layouts, and pioneering reinforced concrete for larger, faster-built open floors. When Keller briefed Kahn in early July 1940, the demands seemed contradictory. The plant had to be large enough for a full tank assembly line plus component manufacture, built in months to meet an April deadline, and convertible back to civilian use after the war. Kahn accepted and threw his firm into the effort, producing drawings through 18-hour days for what became the Detroit Arsenal tank plant, a single-roof structure of 1.25 million square feet, one of the world's largest industrial buildings incorporating 3-foot-thick concrete walls and critical zones designed to withstand bomb impacts. The roof was reinforced with steel trusses, engineered to channel blast forces away from windows and ventilation shafts. The plant's arrangement reflected the Chrysler production concept, a primary assembly line stretching nearly a quarter mile down the building, with feeder lines delivering major assemblies to the main line at timed intervals. Machine shops occupied the north end to produce driveline pieces and precision parts, while welding bays lined the south for fabricating armored hulls and turrets. Materials flowed in a single direction from raw steel delivered at the west end to completed tanks exiting at the east. Kahn introduced one innovation unfamiliar to military planners. The assembly line would sit in a recessed trench about 4 feet deep so tanks could travel on special carriers, letting workers reach the underside without jacks or pits, a modification that shaved hundreds of labor hours from suspension and drivetrain installation. Groundbreaking took place on September 9, 1940. On 113 acres of former farmland in Warren Township, Michigan, chosen for its nearness to Chrysler plants and rail access. Construction began at a breakneck tempo with multiple contractors pouring foundations, raising walls, and installing utilities simultaneously. Reinforced concrete sped the work because sections cured quickly enough to bear loads in days. By February 1941, the main structure stood, though interior systems, windows, and finishes lagged. Despite that, Chrysler started moving machine tools and by rail and installing equipment while construction continued around them, with the factory unlikely to be fully finished before the April deadline. Keller made the audacious call to begin building tanks inside an unfinished shell. That winter produced odd conditions. February and March in Michigan were bitterly cold, and the building had no heating and many missing windows. So workers assembled tanks in heavy coats with their breath visible in the air. A steam locomotive was brought inside to burn and provide localized heat, an improvised but effective solution that symbolized the program's relentless urgency. Technical problems were tackled in parallel. The M2A1's transmission had been designed for hand assembly. Chrysler re-engineered it along automotive lines into a pre-assembled module, cutting assembly from 40 hours to 4. Suspension components were standardized and built on fixtures, so a complete bogie could be made in 2 hours and bolted to the hull in 20 minutes. The armored hull posed the toughest obstacle. Traditional riveted construction required hand drilling and riveting that took weeks and risked rivet failure, spraying deadly fragments inside crew spaces. Chrysler pushed for all welded hulls, meeting Army resistance over untested welding in combat, heat-induced stresses, and the need for skilled welders. Chrysler answered with ballistic-tested welds that outperformed riveted joints, heat treatments to relieve stresses, and production jigs that let semi-skilled workers produce acceptable welds after roughly 2 weeks of training. By March 1941, component manufacture was underway. The first tank, slated for April, would be assembled from parts made in multiple Chrysler plants and trucked to Warren for final assembly. Engine supply demanded creative thought. The M2A1 used the Continental R975 radial aircraft motor, about 400 horsepower. But Continental could not scale output. Engineer Harry Wilson proposed an audacious alternative. Combine 5 existing inline 6-cylinder engines into a single power plant. The resulting 57 multi-bank engine arranged 5 complete straight sixes around a central gear case, each driving a gear that meshed with a central output gear. The assembly produced about 425 gross horsepower and 370 net from 30 cylinders, displacing 1,253 cubic inches. It was complex and unconventionally derided by some in the Army as a Rube Goldberg device, but it reused existing tooling and parts, required no exotic materials, and could be assembled by relatively unskilled labor. Fitting the production timetable the Army demanded, on April 12, 1940, one day before Easter, the Detroit Arsenal plant remained unfinished, with missing walls, windows, and heating. Yet the first Chrysler-built M3 medium tank was complete on the line. The M3 evolved from the M2A1, mounting a larger 75mm gun in a hull sponson and a 37mm in a fully rotating turret. It was a stopgap design that balanced proven elements with urgent need, but it was the first tank produced on an automobile-style moving assembly line. The formal handover came on April 24, 1941, when the completed M3 was driven out of the still incomplete factory before military officials, Chrysler executives, politicians, and workers, with Keller riding in the tank as it emerged. The live demonstration acceleration, obstacle breaches, weapons firing, and even smashing through a mock farmhouse was meant to silence skeptics. What it hid was more consequential: a functioning production system. The assembly line kept running. Component output rose, supplier networks formed, and hundreds of workers learned narrow, repeatable tasks. Production climbed quickly. In May 1941, a tank rolled out approximately every other day. By June, the rate reached 1 per day. By July, 2 per day was routine. Chrysler couldn't make all 8,000 required parts in-house, so B. Hutchinson lead supplier development across Michigan and neighboring states with a blunt offer: meet these specs and quantities on this schedule, and we'll provide technical help, tooling advances, and guaranteed contracts. Many vendors hesitated, but Hutchinson's package persuaded them, and the supplier base grew to more than 400 firms. Across 32 states, a Pennsylvania foundry supplied final drive housings, Wisconsin machine shops produced track pins, and an Ohio forge provided armor plates. Labor transformation, mirrored supplier, expansion. In June 1940, Chrysler had no workers with tank experience. By August 1941, the Detroit Arsenal employed about 5,800 people, most taught from scratch in Chrysler training schools, where new hires rehearsed specific tasks on fixtures before touching real tank's transmission. Mount installers practiced 2 days on rigs before working on an actual vehicle. By September 1941, the Detroit Arsenal was producing roughly 4 tanks per day. The M3 was already proving useful in North Africa under Lindley. British crews nicknamed it the Grant after American nomenclature and praised its dependability while criticizing its tall profile and the sponson-mounted main gun. Chrysler's engineers understood the M3 as transitional and had already begun work on its successor. The gun mounted in the sponson could only swing through a limited arc and made the vehicle taller than necessary. A superior arrangement placed a primary weapon in a fully rotatable turret. In collaboration with Army Ordnance engineers, Chrysler helped develop the M4 Sherman, which became the defining American tank of World War II. The M4 kept the M3's basic hull and suspension but installed the 75mm main gun in a rotating turret. Switching production from the M3 to the M4 showed how adaptable mass manufacturing could be. Instead of stopping the line to retool, the Detroit Arsenal phased in M4 parts while finishing M3 orders. And by February 1942, the line was producing only Shermans. From the outset, the M4 was conceived for volume manufacturing. Chrysler designers changed details to ease production. Hulls used large castings or welded sections that needed little hand fitting. Turrets were cast as single units at specialist foundries. Drivetrains used standardized, interchangeable pieces. And even the tracks were engineered for quick manufacture. The Japanese attack on Pearl Harbor on December 7, 1941, transformed gradual expansion into an urgent sprint. Requirements for armor skyrocketed overnight. The 1,000-tank goal that had seemed ambitious in 1940 was hopelessly small. By 1942, Chrysler sped up output. What had been 4 tanks a day in September 1941 rose to 12 per day by March 1942, and 218 per day by July. Hitting those rates meant constantly removing bottlenecks. A lack of trained welders constrained whole output until Chrysler opened welding schools that graduated about 50 operators weekly. Shortages of machine tools were eased by obtaining prioritized deliveries. Owen Skelton, promoted to general manufacturing manager, created a production expediting organization. Teams of engineers tracked every operation on the floor, found slow points within hours, and pushed fixes through within days. The Detroit arsenal culture became obsessively numerical daily. Totals were displayed for all to see. Shifts competed to outproduce each other, and every worker knew the count for the day, the week, and the month. In December 1942, the plant achieved what skeptics said could not be done. 896 Shermans were completed and handed over that month on average of 29 tanks per day, producing all other American tank factories combined and surpassing the entire German tank industry's monthly output. That result came from relentless refinement. The line ran with clock-like regularity. Vehicles moved from station to station every 55 minutes. Workers perfected narrow tasks through repetition. Suppliers delivered reliably, so inventories stayed low. And quality control became a precise discipline, with inspectors verifying dimensions and fits at every stage. Although subsequent months kept high volume, December 1942 remained the single-month peak for the war, and it proved tank making had shifted from artisanal craft to industrial practice. The Detroit Arsenal's example prompted the Army to seek similar capacity nationwide. Additional plants were built by General Motors, Pressed Steel Car Company, and Pacific Car and Foundry, all adopting assembly line techniques and precision manufacturing, but none matched Detroit's combination of scale and efficiency. By the war's end, in August 1945, the Detroit Arsenal had produced 22,234 tanks, about a quarter of all U.S. tank production during the conflict. Tanks themselves evolved continuously. The Sherman family spawned many variants that incorporated improvements. The M4A1 used a cast hull. The M4A2 employed twin diesel engines favored by British and Soviet users. The M4A3 mounted the Ford GAA V8, and the M4A4 used Chrysler's A57 multi-bank engine. Each change required tweaks to the production line, but the basic assembly approach remained constant. Unlike craft production, which needed highly skilled rebuilds for every design change, line manufacturing only required altering fixtures and updating job instructions. The Sherman's combat reputation is complex. It lacked the armor thickness and firepower of German heavy tanks like the Tiger and Panther, and Sherman crews often faced dreadful odds against those heavier vehicles. Yet the Sherman offered advantages that mattered strategically. It was dependable, easier to maintain with standardized parts and trained repair crews, and most crucially available in overwhelming numbers. Production math underscored the strategic truth. Germany built roughly 24,000 main battle tanks. From 1939 to 1945, Britain, about 28,000, and the Soviet Union, around 105,000. The United States, which only ramped up in 1942, produced roughly 88,000 to 90,000 tanks by 1945, with the Detroit Arsenal contributing roughly 1/4 of that output. Numbers alone only tell part of the story. The deeper change was conceptual. Before 1940, nations treated tank manufacture as specialized military work for government arsenals, requiring years of experience. After the Detroit Arsenal proved the opposite. Tank production was seen as industrial engineering and mass production work. That shift had wide consequences. Industry could be mobilized rapidly. Workers could be trained in weeks instead of years. Supply chains could be spread across continents. And production could be sustained even as experienced laborers joined the armed forces. After the war, Chrysler continued to run the Detroit Arsenal under contract. Tank output paused but resumed during the Korean War, when the plant produced 3,443 M47 patent tanks from 1952 to 1954, later built M60s in the 1960s, and began supplying parts for the M1 Abrams in 1979. Financial strain led Chrysler to sell its defense business to General Dynamics in 1982 for $336.1 million. General Dynamics kept producing at the Arsenal until work consolidated at the Lima Army tank plant in Ohio in 1996. Today, the site hosts the U.S. Army TACOM, Lifecycle Management, Command, and the Combat Capabilities Development Command Ground Vehicle Systems Center, and a historical marker in Michigan commemorates the plant's role. More than 22,000 tanks produced in proof that industrial capacity could be turned into military strength. The leaders in the story had varied destinies. Kaufman Thumela continued at Chrysler through the war and became chairman in 1950 before retiring in 1956. Albert Kahn died on December 8, 1942. months after the arsenal reached its peak production and leaving a lasting influence on industrial architecture. William Cutson served during the war as a lieutenant general, the highest rank given to a civilian appointee at the time, and died in 1948. Shermans from Detroit served everywhere. They landed on the Normandy beaches on DID, fought across Western Europe, participated in Pacific Island campaigns with Marines, and equipped British, Canadian, Free French, Soviet, and Chinese forces under Lindley. Many Shermans survived the war and remained in service for decades. Israel used upgraded Shermans in the 1967 and 1973 Arab-Israeli wars. South American countries operated them into the 1980s, and a number are preserved and still operable as monuments to an era when industrial output determined military power. The shift from artisan tank making to industrial production happened because a small group of engineers and industrialists refused to accept received wisdom. They recognized that an automobile and a tank were both assemblies of thousands of components, and that both could be produced on moving lines by workers performing narrowly defined tasks. That seemingly simple insight was revolutionary. In 1940, it required looking beyond superficial differences, having the engineering courage to redesign military equipment despite resistance, and the industrial confidence to scale untested production methods. The Detroit Arsenal's success extended Henry Ford's mass production lessons into a new domain, showing that interchangeable parts and continuous assembly could produce weapons as effectively as that capability helped change the war's outcome. Without mass-produced tanks, American ground forces would have faced severe numerical disadvantages. Britain would have struggled to recover losses, and the Soviet war effort would have received far fewer American-made Shermans. America's capacity to turn out some 88,000 to 90,000 tanks in 4 years was an unmatched industrial feat, and about 1/4 of that total came from a single plant in Warren, Michigan. Even more important than the visible tally of vehicles was what the Detroit Arsenal demonstrated. Private industry could tackle government problems faster and more efficiently than traditional government arsenals. Engineering judgment could outrank military habit, and when mobilized correctly, U.S. manufacturing was a decisive strategic advantage. That lesson shaped post-war policy. Maintaining convertible industrial capacity became a Cold War cornerstone, and the close relationship between defense contractors and military procurement that began with the Detroit Arsenal contract became a lasting institution. The engineers behind the arsenal practiced systems thinking long before the phrase existed. They did not merely fix isolated issues, they built an integrated production ecosystem in which parts, suppliers, workers, workflows, and quality checks worked as a single coordinated whole. Optimization occurred with the system in mind. The sunken assembly trench removed an undercarriage bottleneck. A geographically dispersed supplier network increased resilience. Training schools created a steady stream of trained labor, and fixtures and procedures were designed so the whole operation could scale. When output needed to double, managers added shifts, expanded supplier orders, and trained more personnel. When a new variant arrived, the line adjusted by swapping fixtures and updating instructions. The payoff was dramatic. The first M3 required about 500 man-hours to assemble. By December 1942, an M4 Sherman could be completed in roughly 150 man-hours, an improvement of more than 300% achieved through relentless iteration. Engineers mined production data monthly, hunted down slow or error-prone operations, redesigned tooling and methods, and constantly asked whether each task could be faster, simpler, or more reliable. That culture of continuous improvement, borrowed from civilian car plants and alien to static military arsenals, proved essential to meet wartime demand. Financially, the enterprise cost a lot up front, about $20 million. To build the facility and another $30 million for equipment and tooling, with total wartime investment topping $100 million. Yet the 22,234 tanks produced represented over $2 billion in output, an enormous return. Strategic value, however, outweighed dollars. The arsenal's output gave U.S. ground forces armored numerical superiority in theaters from North Africa to Germany. And without that capacity, the course of the war could have been very different. The Detroit Arsenal story is ultimately about perception and confidence. When Keller told Knudsen he had never seen a tank, he admitted ignorance but not incapacity. Chrysler's engineers may not have known tank making, but they knew how to assemble complex machines from thousands of parts. Europeans accepted tanks as a special military category, needing artisan skills and dedicated arsenals. American industrialists saw machines to be deconstructed into components, processes, and repeatable operations. That worldview was vindicated. In 9 months, Chrysler moved from zero tank experience to finished vehicles. In 18 months, exceeded expectations, and in 4 years produced more tanks than many nations did during the entire war. The people who made this possible were ordinary workers and engineers doing extraordinary, if unglamorous, work, not beach landing heroes, but builders of the tools that enabled those battles. This democratization of arms production was revolutionary. Where once weapons were the product of master craftsmen in government arsenals, In World War II, they were manufactured in auto plants and a host of civilian industries converted to war work. Housewives, new high school graduates, farmers, and clerks learned narrowly defined tasks and repeated them with precision. The Detroit Arsenal symbolized and proved that shift. Private industry could outproduce arsenals. Civilian production methods could be applied to weapons. And industrial capacity itself was a pillar of national defense. The site's visible artifacts have mostly vanished. Tanks, scrapped or preserved. Buildings demolished, workers passed on, but the methods endure. Modern military manufacturing, from the M1 Abrams onward, traces its procedures to the arsenal's integration of supplier networks, precision machining, and moving line assembly. The transformation from craft to industry that began on those 113 acres permanently changed how states equip forces. Engineering expertise could overcome supposedly insoluble problems. Production principles from civilian life could be applied to complex military systems. And when mobilized, American industry could outproduce any foe. That invisible weapon, the ability to treat warfare as an industrial problem and solve it systematically, helped win World War II. Kaufman Thummer Kellers. Candid, I don't know, on that June 7, 1940. Call was less an admission of failure than the start of a promise. We'll figure it out. Engineers, workers, and suppliers answered that promise by designing a production system that made tanks roll off an assembly line like cars, proving that complexity did not preclude mass production, and that bold industrial thinking could turn the impossible into reality. The arsenal's greatest legacy is not merely the machines it produced, but the demonstration that engineering confidence, systematic organization, and industrial scale can solve problems others call impossible. When someone declares something can't be done, the right response may well be, "Show me why not, and let's figure it out." That attitude